Hi, chemistry. We're going to talk about balancing chemical reactions today. Now, balancing chemical reactions can be kind of a tricky skill, but it's a really necessary skill to learn when going through chemistry because of the law of conservation of mass. So, the law of conservation of mass is something I bet you guys already know. And this would be a good time to pause the video and see if you can write out as much of the law of conservation of mass as you can. Okay, so what did you write? The law of conservation of mass states that in a physical or chemical reaction, mass is conserved. Okay, so let's break this down a little bit. Notice it's in a physical or chemical reaction. So the law of conservation of mass is actually not true in a nuclear reaction. In a nuclear reaction, there is another law called the law of conservation of mass and energy. So it's actually only true for physical and chemical reactions. And what it states is that mass is conserved. So to conserve something means to keep it the same. So if mass is conserved, that means mass is not created and mass is not destroyed. So as a chemical reaction proceeds forward, we're not actually creating any mass. We're not gaining any matter. And we're also not destroying any mass. We're not destroying any matter. So basically what this is telling us is that whatever mass we start with at the beginning of the reaction, we also need to end with that same mass. And you can see what I'm talking about here with my little example on the board. You can see that I have a reaction here. H2 plus O2 goes to H2O. Now, notice that I have two H's, right? So we're going to revisit subscripts in here in just a minute, but remember that subscripts tell me the number of atoms that I have. I also have two oxygens, one oxygen molecule that contains two oxygen atoms, and then those two combine to make a water molecule. So the water molecule, as I have it written, is one oxygen connected to two hydrogens. So as I have the reaction written, do I have the same amount of matter on both sides of the equation? Notice that I have two hydrogens on the reactant side. I have two hydrogens on the product side. Okay, so that lines up. Now here I have one oxygen on the two oxygens on the reactant side and only one on the product side. So this oxygen seems to have disappeared. Where did it go? Well, it seems to have disappeared because this is not a balanced reaction. We need to balance this reaction to make sure that whatever mass we start with on one side of the reaction is the same as the mass that I end with. If I start with two oxygens on one side of the equation, right, oxygens weigh 16 grams. So I have 32 grams of oxygen on one side of the equation. Well, I need 32 grams of oxygen on the product side of the equation as well. And that way I am following the law of conservation of mass, which is true for any chemical reaction. So I'm going to teach you how to do that today. Now, this is a chemical reaction, and this is actually how we've been writing them until now. A chemical reaction that's unbalanced is called a skeleton reaction. Okay, it has reactants, it has products, it has all the necessary components, but it's unbalanced. There's more mass on one side of the equation than there is on the other. So we are going to talk through how to balance equations today. But before we do that, let's kind of touch base on a couple more concepts. All right. First of all, indications a chemical reaction has occurred. So we talked about this way back at the beginning of the year. How do we know if a chemical reaction has occurred or not? Pause the video here, see if you can list off a couple possible indicators that you could observe that would tell you that it might be a chemical reaction. All right, here are a couple things you may observe as you watch reactions happen. And if you see these, it may be a result of a chemical reaction. It's not for sure because we'll go through these, and as you can see, some of them can be kind of tricky. So first of all, a color change. If your solution started purple and ended clear, that is an indication that a chemical reaction has possibly occurred. Now, you have to be careful of color changes because it could just be colors mixing. So, for example, if you have one substance that's red and another substance that's blue, and you mix them together, you're going to get the patriotic color of purple. That's not a new color. That's just red molecules and blue molecules so close together that your eye can't distinguish between them. Right? The color is still there. The red's still there. The blue is still there. It can actually be separated out again. You're just seeing a new color, but there's not actually a new color there. So you have to be careful with color change. Temperature change is another indication that a chemical reaction has occurred. Again, you have to be careful with this one. If you drop a hot object into cold liquid, the temperature of both things are going to change. Doesn't mean a chemical reaction occurred. But if you dissolve a salt in some water and bonds break or form or mix around, then that could be an indication that a chemical change has occurred. Gas formation. If you form a new gas that wasn't there before, similar with color and temperature, a new gas that wasn't there before, that is an indication that a chemical reaction may have occurred. And then same thing with a precipitate or a solid. If you form a precipitate through a reaction, a new solid that wasn't there before, that is an indication that a chemical reaction could have occurred. So these are possible indications of a chemical reaction, not a guarantee, but they kind of give you some foundation to start to watch and observe in order to determine if a chemical reaction has happened or not. All right. As you're looking with chemical equations and you're working with chemical equations, we've talked about a couple symbols that you might see, like the plus sign and the arrow. There are other symbols also. First of all, there's symbols that tell you what the phases are. So if your substance is in the gas phase, you'll see a G in parentheses. Liquid is going to be an L in parentheses. Solid will be an S in parentheses. And then there's one more you might see, which is AQ. AQ means aqueous. And what that is it's something that has been dissolved in water. And actually in chemistry, we do a lot of reactions where things are dissolved in water. So you'll see this AQ quite a bit. The other symbols that you might come across are symbols that you will see above the arrow. So if you see some molecules or elements or formula units in your reaction, These are the reactants and the products. These are the things that are actually involved in your reaction. If there's something present that's really important that's not involved in the reaction, it's not actually changing, you're going to see that above the arrow. So you might see things like a triangle, and that means that heat is involved. You might see H2O, that indicates that the whole reaction happens in water. That would also be indicated by the aqueous phase symbols. And then you also might see a compound above the arrow. If you see an actual compound or molecule above the arrow, that's going to be something called a catalyst. It actually is not involved in the reaction. It doesn't change. It's there in the beginning, it's there at the end, but a catalyst is going to speed a reaction up. It's going to change the reaction rate. So the catalyst might actually be very, very important. The reaction might not actually happen within your observable lab experience, or perhaps not even in your lifetime, without a catalyst present. So if there's a molecule that needs to help the reaction occur, but it's not actually going to change throughout the reaction, you'll see that above the arrow as well. And so these things typically get written very small, and they are literally right above the arrow. So it's not a reactant, it's not a product, it's just important for the reaction to happen. All right, so as we balance reactions, let's go back to this one. Okay, so subscripts. We have been dealing with subscripts since we've been dealing with bonding. Remember, subscripts tell you the number of the thing that's present, but it's only the number of the thing that it's directly behind. So like this 2 in H2O is telling me that I have 2 hydrogen atoms. It says nothing about the oxygen. Same thing if it's written behind something in parentheses. Remember that that subscript is describing whatever is in the parentheses. So I would have like 1 magnesium attached to 2 nitrate bundles. Right? So here's a nitrate. Here's a nitrate. I have 2 of them because I have 2 of whatever's in parentheses. Okay, so we know what subscripts are. We know how to deal with them. When we are balancing chemical equations, we are not going to touch the subscripts. The subscripts tell us about bonding. So if you change the subscripts, you're going to change how that bond is formed. We don't want to do that. The very first thing we do when we're writing a chemical equation is we determine molecules or compounds. We have to determine what the reactants and products are. After we determine what the reactant and product compounds are, then we balance them. So this first step is done with the subscripts. And then you don't touch the subscripts after that. Once you determine what those compounds are, you can't change the subscripts, or you end up changing the compounds. So rather than changing the subscripts to balance the reactant and product side, we're going to change the coefficient. So a coefficient in chemistry is the same thing as a coefficient in math. The coefficient in chemistry and math is going to be a big number. It's going to be in the beginning, and it tells you the number of whatever follows. It's going to tell you the number of whole molecules or whole formula units. It's not telling you the number of the thing it's directly in front of, like the coefficient. Let me show you an example. If I write H2O, I'm telling you that in this molecule, I have 2 hydrogens bonded to 1 water, right? If I change the big number in front, or the coefficient, I don't change that bonding at all. I just now have 2 of that exact same molecule. If, in contrast, I started with H2O and I doubled these things, so I end up with H4O2, what I've just done is now I have 2 oxygens and 4 hydrogens all bonded together. So subscripts indicate bonding. You don't want to change the subscripts when you're trying to double the entire molecule. We're going to use a coefficient for that. Okay, so coming back to this equation, I need to get the same number of hydrogens and oxygens on both sides of the equation. So in order to do this, I'm going to follow a certain procedure that will help me count as I go. So I'm going to write the number of hydrogens I have on the reactant side and the product side. So I have 2 hydrogens on the reactant side. I have 2 hydrogens on the product side. I have 2 oxygens on the reactant side. I have 1 oxygen on the product side. Now, by doing this, I'm keeping track of things, and I can clearly see now that my hydrogens are balanced, my oxygen is unbalanced. Remember, I can only change the coefficients. Okay, so I need more oxygens. I'm going to add a coefficient here of 2. Now I have 2 water molecules, right? I had 1 water molecule. Now I have 2 water molecules. So I have 2 oxygens now, but I also have 4 hydrogens. So I just screwed up my balancing for the hydrogens, but that's okay. You're going to do that as you balance these equations. You're going to unbalance one, and then we circle around and rebalance it. Just keep trying, and you'll eventually balance everything. Okay, so my oxygens are balanced now. Now I need to revisit my hydrogens. I have 4 on the product side. I have 2 on the reactant side, so I'm going to double this. Now I have 4 here. Hydrogens are balanced. Oxygens are balanced. I am done. This is my balanced equation. And if we go back to the molecular view, right, I have now 2 molecules of hydrogen. I have 1 molecule of oxygen. And I have 2 molecules of water. Okay, so you can see I have 2 oxygens on the reactant side. I have 2 oxygens on the product side. Those are balanced. I have 4 hydrogens on the reactant side. I have 4 hydrogens on the product side. Those are balanced. So this is how we balance equations. We don't mess with the subscripts. Once we have written out the compounds and figured out what they are, we don't mess with the subscripts anymore because we don't want to change the bonding. We do change coefficients because coefficients will double the entire molecule that they are in front of. And we keep track of the numbers that we have, and we just play with them until I have the same number of atoms on the reactant side as the product side. That is a balanced equation. The mass is conserved. Okay, so let's try a couple more of these together. Okay, let's try zinc hydrochloric acid goes to hydrogen gas and zinc chloride. Okay, so pause the video here, try the steps we just went through, see how it goes. Step 1, did you take inventory? Zinc, hydrogen, chlorine. How many do you have on both sides of the equation? If you haven't done that yet, pause the video and do it now. So I have 1 zinc and 1 zinc, 1 hydrogen, 2 hydrogen, 1 chlorine, 2 chlorines. I can clearly see now what's balanced and what's not balanced. So now we play with coefficients in order to balance it. And I can start with hydrogen or chlorine, it doesn't matter. And actually they're stuck together on this side, so I can play with both of them at the same time. And make this a 2. That changes the number of hydrogens I have, changes the number of chlorines I have. Oops. And now everything is balanced. This is my balanced chemical equation. Did you beat me there? One thing to notice is in front of the zinc, notice it's blank. If it's blank, just like with subscripts, if it's blank, we assume it's a 1. Same thing with coefficients. If it's blank, we assume it's a 1. Right? Okay, one more example. I want to do this, a similar one, with a polyatomic. Okay, so very similar thing. When I set up my inventory, you can just separate everything out like that and it will work. But with polyatomics, if they are the same, if the polyatomic hasn't changed, you can actually keep it as a bundle. So notice NO3 is a bundle here, NO3 is a bundle here. I don't have to separate them out. I can actually keep them as a bundle and count them as a bundle, and it simplifies my life a little bit. So notice I have 1 zinc, 1 zinc. I have 1 hydrogen, 2 hydrogens. I have 1 nitrate, 2 nitrates. So instead of having 1 and 3, 2 and 6, right? Instead of having these numbers, I have just a 1 and a 2. Just simplifies things a little bit. And then you can clearly see that I need to double the nitric acid to 2, and everything is balanced. You can separate it out. It will work. It's just a little bit more effort. So if you have polyatomics and the polyatomics don't change between the reactant side and the product side, yes, it's bonded to something different now, but nitrate's still a bundle, right? It's even being doubled as a bundle. So you can just keep it as a bundle that you count and you don't have to separate it. Okay, so let me know what questions you have. We will practice this together. I will see you in class.